Hello, student. How are you, everyone? I hope everything is all right and everything must be fine with you. So, students, today we are going to understand a very important topic, and that is your Bernoulli's equation, right? It's a part of the fluid mechanics. So, let me just, quickly explain you about Bernoulli's equation. So, before Bernoulli equation, we should have some idea. This Bernoulli's equation will come under the category of dynamic fluid because when we, start studying this particular chapter, then we simply divide it into two parts. The first one is static fluid and another one is dynamic fluid, right? So whenever we are going to study dynamic fluid, so before Bernoulli's equation or Bernoulli's theorem, we should have idea about when we can apply the Bernoulli's equation. So there are some, assumption which we have to assume. The first assumption is fluid must be, everyone, fluid must be non-viscous. Non-viscous. Sir, what do you mean by non-viscous? Which means we won't consider any friction, fluid friction, because viscosity is what? It's basically a friction in fluid or friction in liquid, right? Second one is fluid must be non-compressible. Non, in actually fluid is non-compressible, that is true, right? So these are the two assumptions which we have to consider before applying Bernoulli's theorem, right? That we are not considering any viscosity and fluids are non-compressible. We cannot compress the fluid, correct? Yeah. Now, so I was saying about Bernoulli's equation, everyone. So let's assume, everyone,
We are having
this kind of structure. Just a sec. Yeah. This kind of pipe, let's suppose guys, we are having something like this, right? Something like this, right? Correct? Yeah. The area of cross section here and here are we are considering same, right? It's not different, everyone. So now the topic is obviously Bernoulli's equation, right? Or you can also call it Bernoulli's principle, correct? So what I was saying is, everyone, let's suppose this is the ground surface, correct? And this height is given, which is h1, and this height is also given, which is h2, correct? Yes, sir. Now, everyone, let's suppose liquids are flowing from this point. Let's suppose we are considering this point is A and this point is B. It is flowing from this point to point A to obviously point B, right? Yeah, something like this, right? Correct, sir. So if you will see very carefully, everyone, then you can say, sir, at this point of time or at this point, we can say, sir, fluid is moving just because of the pressure. So let's suppose at this point, we are considering the pressure is P1. At this point, we are considering the pressure is P2, right? And at this point, let's suppose the velocity is V1. And at this point, let's suppose we are considering velocity is V2, right? Correct, sir. So the height is h1 and this height is h2, obviously. So everyone, what we are thinking about, how to derive the Bernoulli equation. So our answer is very simple. Basically it's an energy conservation, right? Or because if we will be considering all the forces conservative, then we can simply say it's an energy conservation. Or we all knew about work energy theorem. Work energy theorem, right, everyone? What is energy theorem? So work done due to all the forces, work done due to all the forces is equal to change in kinetic energy. Work done due to all the forces is equal to change in kinetic energy, right? So let's simply apply this. So let's try to understand, sir, work done is happening because of how many of forces? So let's just consider, or let's just look at into this, that how many forces we are having. So if you'll see very carefully, everyone, then this liquid or fluid is moving from point A to point B. So if it is moving from point A to point B, then if you will see, sir, because it is moving from point A to B, then obviously there is work done due to gravity. So the formula is work done due to all the forces is equal to change in kinetic energy. So work done due to gravity plus. Is there any other forces? Answer is yes. Sir, work done is also happening because of this pressure difference, right? So I can also call it, sir, work done due to pressure, right? Is there any other force? I don't think so, right? Because we have considered the gravitational force, we have considered the work done due to pressure is going to be equal to change in kinetic energy is going to be equal to delta K. Now, one by one, from one by one, we are going to understand what is work done by gravitational force and what is work done by pressure, right? Okay, in the next slide. So if you'll see, work done due to gravity is going to be equal to, sir, if you will see in the previous slide, sir, liquid has been flown from this point to this point. So obviously this is going to be equal to, sir, H2 minus H1, right? So H2 minus H1, so the total force which is, exerting through this liquid is going to be equal to mg, which is in downward direction, right? And height difference is our h2 minus h1. This is basically displacement, force into displacement, into cos theta. What is theta? So angle between this force and displacement. Now if you will see very carefully, then this force is acting in downward direction but displacement is in upward direction. So I can say, sir, work done due to gravity, we have got minus of mg h2 minus of h1, right? First thing is completed. Now let's have a discussion about the second thing. And what is the second thing? Sir, work done due to pressure. If you'll see very carefully, sir, work done due to pressure, right? Pressure at this point is we have got how much? Sir, P1. At this point we have got how much? Sir, P2, right? So what will be the pressure difference? Sir, P1 minus P2, right? Because obviously pressure at point A is greater compared to point B. So, sir, P1 minus P2. And we all knew that, sir, the pressure difference we have got. Now, sir, what will be the next term? Sir, change in volume, delta V. Because the work done is going to be equal to P into delta V. Correct? Yes, sir. Now, sir, what is this volume? Let's suppose we are considering a very small, portion from this liquid. Let's suppose we are considering from this point to this point. So if this is gonna be your change in volume, right? So this at this particular time, liquid will flow from here to here, and again this is volume is going to be equal to delta V only. Correct? Absolutely, yes, sir, absolutely. Now, so work done due to pressure, we have got P1 minus P2 into delta V. This is your equation number 2. This is your equation number 1. Now, what was the work energy theorem, everyone? So the work energy theorem was, which we have written, work done due to gravity plus work done due to pressure is going to be equal to change in kinetic energy. Now, work done due to gravity we have found, which is minus of mg h2 minus h1, correct? And work done due to pressure is we have got P1 minus P2 into change in volume is going to be equal to 1 by 2 mv2 square minus of 1 by 2 mv1 square, right? Correct, sir. So this equation is going to be equal to minus of mg into h2 plus of mg into h1 plus of P1 into change in volume minus of P2 into change in volume is going to be equal to 1 by 2. Now, this M, sir, we want to find the equation in the form of density because density is given. Density of the liquid is given, not mass is given, right? So let's suppose we are considering only for the this liquid, right? So that is going to be equal to P1 minus P2 into change in mv2 square. So m is going to be equal to rho into, and for the how much volume we are considering, so delta v, obviously change in volume, right? Rho into delta v, right? Into v2 square minus of 1 by 2 rho into delta v into v1 square. Now if you'll see very carefully, everyone, we are having m here as well. So let's consider this is also going to be equal to rho into delta v because liquid same, rho into delta v. So if you will see, so delta v is common and cancelled in both sides. So eventually it is going to be equal to minus of rho g h2 plus of rho g h1 plus of p1 minus of p2 is going to be equal to 1 by 2. rho of v2 square minus of 1 by 2 rho of v1 square. Correct? Yes, sir. Now, eventually, finally, what we can write is, sir, p1 plus rho g h1 plus 1 by 2, this half rho v1 square will come in this side. Half rho v1 square is going to be equal to p2 plus rho g h2 plus half rho v2 square. Simple. And this is your Bernoulli's equation. Correct, everyone? Right? We can also write it. So P plus rho g h plus half rho v square is going to be equal to constant, right? It's something like P1 v1 is equal to P2 v2 is equal to P3 v3 is equal to. So obviously P and V is constant. In a similar way, we can write P plus rho g h plus half rho v square is going to be equal to constant. So everyone, this is your Bernoulli's equation, right? This is your what? Bernoulli's equation. So I think again a very important thing, right? When we can apply the Bernoulli equation, when sir the fluid is going to be non-compressible and sir non-viscous, right? Only in these two must be verified first. Only then we can apply the Bernoulli equation and then we will be solving it. So I hope everyone you have liked this Bernoulli's equation lecture. That is it. That's it from my side. Thank you so much.